The unique advantage that we have at
All right, I think we should be good now. Yeah, sorry about that. Just had to get everything lined up. Let me go ahead and tweet out that we're live for a second. Hmm. Share a link via Twitter. Okay, man. Having to always tweet out that I'm live, it's kind of a pain in the ass. But all right, let's go for it. In the meantime, let's actually take a look at Hacker News and see what interesting shit happened today. Sequoia Fund. Former Facebook staffers launch Integrity Institute. Hold up. Now they want the world to know how it works. The team Facebook Papers whistleblower. Okay. The report revealed some genuinely horrifying findings about the troll farms. Okay. So apparently, Facebook promotes all these troll farm content. Okay. I mean, I think that's pretty interesting, but I think most people kind of already knew that. So my question now is like, what's gonna happen? But you want to write Python scripts and anonymously regurgitate content into communities while siphoning some monetary or influence reward for yourself. All right. So they've tried to actually deal with it. And so he is finding a okay, so it's the last 10 months, he and Sahar, another former Facebook staffer who helped the company's election and civic integrity teams from the earliest days, have been creating an independent organization that can help the entire tech industry answer questions about integrity. All right. All right. So looks like it's just an announcement of a particular what's it called institute that they started. So I'm not quite sure what I wanted to get out of this just yet. Okay, so basically, Francis exposed a lot of the knobs in the machine that is modern social media platform. Now that people know how these knobs exist, we can start having a conversation about what the science of these work, what these knobs do, and why you want to turn them in what direction. Okay, so at least you understand the kind of work they do, but it's like, to me, that doesn't really add any value. It's just mining the efficiency out of your users by playing with their behavior. And to me, that's not something that I think is a good way of doing business. So I think the rest of the article is just more or less kind of like the same thing. A guy, I guess, diving into the details. But let's see. Debunked it. Airbnbs have spent their days co-working space trying to come up with a consensus on questions that only a geek love but matters for billions of people. If a user doesn't follow a specific account, should they ever see posts from that account in their main feed? On Facebook, it happens all the time, yeah. Alan's own research at Facebook shows how troll farms exploit Facebook's ranking algorithm to get mass exposure on news feeds of people who don't even follow them. At the same time, some in the group argued that in the best scenario, this can be a way for platforms to share more high-quality content with users who naturally follow low-quality content, sure. The thing is that with high quality content, it tends to be a little bit drier and more boring. I mean, there's only so much quality that you can pack into something that is only going to be like a 5-minute snippet or whatever, or some small summary of what you're trying to convey. Like, for instance, how do you convey like, for instance, if I'm talking about like physics, right? I might be able to present to you one equation, like maybe Newton's first law. But even then, that's like a small microcosm of the entire world of physics, right? And so because of that, it's like, just because you see that doesn't make you a master at physics. It informs you about like one little area of physics, and it's like you don't even get a chance to apply it. So are you really quote unquote a physicist at that point? So it gets to the whole point of communication and how efficient your communication can be when you have when you're dealing with such a small, like when the amount of quantity of information that you can deliver is so small, it's just impossible. So it's kind of like why low quality content that is disseminated for the masses is very easy to ship out. It's just very easy to consume, actually. So let's write the numbers, blah blah blah. Okay, so it's like the whole dynamic is about integrity versus growth. I think that, yeah, I think that's pretty much the battle. That's pretty much the battle. How much can you make? How much more money can you make versus like the ethics that you run into? And of course, like, it's not up to Facebook never signed up for that ethic battle, but now it finds itself having to deal with that. And to me, it's just like it's a very hard question to answer, both from their perspective, the human perspective, and from Facebook's perspective as well. So, okay, let's see what else they got. Ask Delphi. Okay. Oh, this is gonna be fun. Descriptive ethics. All right. This seems very susceptible to the wording used. I think the responses are just looking for common phrases or patterns. All right. Wow. Okay. Wow. The instant if I was like monetized, this would instantly be demonetized. But Jesus Christ, stealing bread if I'm okay. Hold on. Stealing bread if I'm poor apparently is okay to ask Delphi. Let's actually try this. Ponder if stealing bread if I'm... Holy shit! It actually said it's okay. Okay. People in the chat, like, tell me what else I should put into Ask Delphi, man. Like, this is actually kind of hilarious. You can... I mean, not the fucking dilemma, but, like, holy shit, I bet you we can actually use... we can actually just trying random shit, and then it'll come up with some outrageous statements, you know, or like something weird. Holy shit. Okay. It's also influenced by previous answers in the same session. Huh. Sort of like humans. Frank Lunt's use of language. Okay. Okay. No. Delphi is learning moral judgment for people who are carefully qualified on mTurk. Only the situations used in the questions have been harvested from Reddit as a great source of ethically questionable situations. Fair enough. mTurk is pretty much worthless in these situations. Okay, I don't even know what mTurk is. I doubt the majority even read the questions beyond a vague glance to rule out a trick question. It's also biasing answers towards cultures that A, are primarily put in places that mTurk pays out, and B, are primarily in places where the cost of living is low enough that MTurk can provide a job. Well, what the hell is the MTurk, actually? Well, let's actually Google this. Oh. It's a crowdsourcing website for businesses to hire remotely located crowd workers to perform discrete, on-demand tasks that computers are unable to do. So basically, they contracted out the ethical reasoning for this machine. Are you kidding me? They're qualified contractors. All right. Not sure I'm trusting random people on the internet to do moral judgments for me. I think that's pretty much what this amounts to. I mean, it's a cool project, but it's like, not really here. I'm not sure I get it here. Whoa. Is it okay to run a corpse through a wood chipper if it creates jobs? Holy shit. Wait. Let me see if that's even... What? Is it okay to run a corpse through a wood chipper if it creates jobs? It's okay. What the Oh my god. Alright, I think we officially broke the bot. I think we broke the goddamn bot here. Oh, the FBI's internal guide for getting data from AT&T, T-Mobile, and Verizon. Okay. So how do you actually get data from freaking companies? Okay. The document, a 139-page slide presentation dated 2019, is by the FBI Cellular Analysis Survey team. Okay, so it's analyzing tower dumps. Can they actually do this? Introduction to Basic Cellular Theory, Cell Towers. Huh. So they actually just go up to these cell towers and actually just mine the data from it? Jesus. Okay, so they actually have a way... Is this legal? I'm pretty sure this is not legal, dude. Like, Verizon hold it for what? So AT&T actually holds on to fucking data for 7 years? Are you kidding me? How to obtain location data from burner phones. Wow. Okay, so Cricket Wireless is actually a subsidiary of AT&T as well. Wow. Today I learned. But I think this is really interesting, like how much data these cellular providers actually hold on you. I think it's kind of interesting. TT doesn't validate results, so I'm actually it's okay. So they actually have a whole slide, and I think if you want to see it, you can look up the post on Hacker News. But I think it's kind of scary. That shit's kind of scary, man. All right, I think it's pretty close to time. Let me go get my client, and then we'll get started.
Recording in progress.
Hey man, what's up?
Hey, Edbert.
Hey, how's it going?
Going good. How are you?
Hey, I'm doing all right. Yeah, catch me up on everything that you did over the weekend, and if you had any issues.
Yeah, for sure. In terms of issues, not particularly, no. Just basically right now, reviewing like the mistakes, per se. And yeah, not that many issues, I think, other than just kind of like the typical like studying and whatnot. So yeah.
Okay. I saw that when we did our check-in on Saturday, you had some issues with like doing recursion.
Yeah.
Yeah. And then like I told you to do like the follow-ups and stuff. Try to walk through your idea before you commit through it. Yeah. So like, how has that actually gone? Do you feel like it's gotten better? Do you feel like like overall, has it made your practice a lot better? What do you how do you feel right now?
Yeah, so in terms of for like the follow-ups, if I had to be honest with you, the I haven't had time to review the mistakes yet,
Okay.
like all of them per se. Just only the kind of uh the ones that like I kind of have in my interview diary, the practice diary,
Okay.
that I've gone through. But in terms of just kind of like the follow-ups or like the so yeah, I think that's kind of just where I'm at right now, with regards to the follow-ups. But
Okay.
yeah, in terms of just, I think the main issue was just kind of like when I'm doing the testing for the recursion, I was doing this replay to, I guess this morning when it comes to passing in like inputs and whatnot, and just not feeling like I fully understand like the idea. Like I get flustered when I'm passing that in. So I think that's just like one kind of issue I noticed. But other than that, I think um, that's pretty much it. Yeah.
Okay. So basically, you're struggling with actually drawing the recursion stack. Is that what I'm hearing?
Yeah, yeah. Like for example, like the pat sum kind of problem, right?
Okay.
Let me just to kind of give you a brief example. When it goes for like all paths for a sum, when I'm passing in kind of like the array of like all the paths, right?
Okay.
Or and also the just keeping track of what it is. Like I understand the concept, but the minute I start implementing it, I start like kind of like second guessing myself and like kind of like adding it in or whatever the case might have you like updating the sum and whatnot.
Um,
Uh,
I would need
and
to see
so
you actually do it in person. I don't understand quite what you're saying.
okay, for sure, for sure.
Do you have like
But yeah,
a live example that I can see?
yeah, for sure. Let me send you the Zoom link real fast for
Okay.
in the Google Doc.
Sure.
Mhm. Yeah. So if I send it to you here in the Zoom chat. So if you go into the Google Docs, right on page, I believe, 4, there's the replay analysis. Yeah.
Okay. Replay analysis. Page 4. Okay. Got it. Got to see it.
Yeah. And I kind of already put some notes, but I think around 17.0 is when I start like stumbling on the recursion.
All right. Let
Um,
me let me go ahead and watch this a little really quickly.
yeah, for sure.
Get past the sum. Um, I'm just gonna skip through it
Sure.
because I want to get to the point. You said it's like at about 40 minutes.
17 minutes, 17 minutes.
Okay. So let me go to 17 minutes.
Yeah.
Okay. So no current sum 1. Sure. Current path 1. Current path 1 7. Sure. Okay. So current sum is 4. Sure. So then now you're going to node 4. Current sum path 174. Current sum is 0. Results 174. Okay. Cool. I think you're doing this fine. But then now you like the thing is that now I want you to erase this and pop out of the function call stack because that's effectively what you're doing. So I would say you need to delete the 4 current path. Does that make sense?
Can you share screen real fast? Sorry. Or I guess I can for current path.
So I'm showing you right here. Do you see
Yeah.
it? Yeah. So here
Yeah.
you're basically simulating the function call stack, correct?
Right. Yeah.
So once you're done with processing node 4, you need to evict this. You need to pop it off, right?
Yeah. Yeah.
So I would like, it's like in the future, I would definitely want you to eliminate this. And then also you say results. Well, results technically is a global variable unless you're passing it in through everything. I'd personally make results global so that I'd keep it outside the function call stack.
Okay. I see.
Just to represent it. Yeah. So okay, I get what you're doing here. I think it's fine so far. Let me
Okay.
speed it up.
Yeah.
So right now, right, is this the part where you're actually having problems?
I think this is like an issue I need to address, but with each one of them.
Okay, so pop node onto the current path. Um, I would say push node, but yeah, sure. Subtract from current for node val upon reaching a leaf node. Check the value is valid equal to sum. If it is, push path. Yeah, I would say current path just to keep it a little bit more the nomenclature a little bit better onto global return array. Sure. I would say again, like keep it to the final like return list or something like that. Final answers. It's like these little language things are like I'm being a little bit nitpicky, but it also can help because global return arrays, like why are we putting things in array? The moment you start being a little bit off detail, you're not as succinct with your naming and what these are, then it's just like it's gonna lead you to some confusion. I think that's one part of it, but then
Got you.
again with pop.
I guess yeah. I guess the issue more so is the I guess in the terms of looking at the pseudocode right now, it's actually like kind of clear, like kind of what's going on.
Yeah.
Including if the testing's not like that great.
Uh-huh.
But like, I think it's more so the implementation. Actually, I think that's the part where I was getting nitpicky on. Because I think when I'm writing out the code, when I compare it to like the optimal kind of solution, it's just kind of they do this thing where they delete it, and this is kind of me being like worrying more about like the final result, I guess, rather than like the preparation for it. But it's just like I'm not sure how much that would matter, but that's just something that's been bothering me at the back of my head. I think, yeah.
That's fine. If that's is that like I want to give you as much value as possible in the time we have. So my question is that what you find is like your biggest issue when you've been practicing, or are there other ones?
I would say that's in terms of for recursion specifically for like DFS. It's the final kind of implementation, I think. Yeah, like part. But I assume there's like I just don't think it can be the final implementation that's the issue. You know what I'm saying? Like
yeah, I get what you're saying. And basically what I'm seeing here is that it's not your approach is fine. I'd be a little bit more atomic about it, but I think it's fine. Let me see how like the way you write the code.
Yeah, because I introduced this current sum thing, right? But the actual like solution doesn't have like the current sum where I'm like, like reversing and whatnot. So yeah.
Okay, that's fine. It's like let me. Where is a timestamp that I can see the final code that you write?
Give me a second. Sorry.
I also think it's a little. I think this problem should have taken you only 25 minutes to do, or 25 minutes. So I'm hoping that by 26 minutes, do I see? Yeah, you're definitely second guessing yourself a lot. Did you find that after you second guess yourself, you are making a lot of changes?
This is me. Yeah, it's not necessarily changed, but I became like very unsure about myself. Yeah, I think.
Okay.
Give me a sec. Let me find the actual implementation part for you.
Yeah, I'm trying to look at this, and I'm just like,
I'd say go to 35. I think that's where it's starting. Yeah, right now.
Okay, this is gonna be a good replay to look at later, but
okay, sure.
Like for Thursday, we can look at this one as well.
Yeah.
But okay, yeah. So basically, what they're doing, it's fine, because what they're doing is they're passing in the current sum, and to each what's it called into each recursive layer, right? So they're taking off the current value. That's fine. And then what you're doing, let me see what you're doing here. If current sum is 0. Yeah, this is fine. It just having that little value, it does. This is like insignificant. Like, if you're able to remove values, it's fine. I think it's fine. Don't worry about it. Like, in their solution, if they're making required sum minus to no value, not a variable, and they just pass it in, it doesn't fucking matter.
Okay.
It literally like whether or not they put it as a variable out here or they put it in here, it doesn't fucking matter because as long as you get the idea right. It's good enough. What I am concerned is that your code seems a little bit more verbose, but I think this is fine.
Yeah,
it looks a little bit different, but I think if you did you try copy pasting this and running it?
No, because I looked at it and I kind of was just like, it seems there, but what essentially was tripping me up was the current sum, like what I was doing with backtracking with the like current path. I was also applying to the current sum. But the optimal solution wasn't doing that. It wasn't backtracking in regards to the current sum, so I was just like, yo, I feel like it's flawed.
Okay. So the thing is that the current sum is what they're passing in is a copy, right? They're creating a new integer.
Okay.
And so your current sum is you're constantly managing it. So what you did actually, you did more work. Their answer is not flawed. What you did is that because you created this variable, and then you did this current sum and then backtrack it unnecessarily, you could have just gone ahead and just made a copy of that integer and just did what they did.
Okay.
It's because you have this reference here, but it's I would say the problem here is that keep in mind like when you pass an integer in, it makes a copy. It's not a reference. So
Oh, it makes
that's
a
your
copy
issue.
of it.
Yeah,
Okay, so it's
you
not
make some
returning
pass by
back to
reference
you.
versus pass by value. That's why I said you have to run it. You have to run it.
Okay, got you.
So
Okay,
I'm gonna write that down. Pass by reference versus pass by value.
okay, yeah.
You're pretty close. Like at least you got there. All that's left is just a technical calculation that was wrong. So
hmm
try this Python. But if you got that far, then I think it's pretty good. I
Yeah,
would
I
say.
mean, to be fair, like I've definitely seen that problem before,
Oh,
but like I did like step through the entire thing, so
mhm.
it was just maybe like that ending part, yeah. So
It's also that it's like when you got to 25 minutes, I would have expected you to be done with the code actually. But the fact is you spent an extra 10 minutes, and I'm curious why. Give me the brief executive summary. Why did you have to make change? Why did you have to keep testing? And did it end up in actually changing your pseudocode?
no, I think I was just running through the whole thing. I
Okay.
mean, maybe it was just like me second guessing when it came to like the current sum or like current path stuff, but in all honesty, it was just me testing, I think, because
Okay.
like doing all the
So it's
reverting
you
and
being
stuff.
paranoid about testing mostly, but you didn't make any
Yeah.
changes to your pseudocode.
Yeah, no changes to pseudocode, yeah.
Okay, that's fine. Like I'm okay with that actually at this point. All we need to do now is just make sure we understand what exactly constitutes good testing. But if you can, like, you basically, I would count this as a win because you got the pseudocode right on the first try. And if you understood how to test it a little bit better, or you got a little bit cleaner at the approach, it would have been a 25-minute problem,
Got you.
and that would have been great. So I've not seen it before, but like I think if I were to actually listen to this, I'm pretty sure you would have been able to explain it pretty well. So that's fine. Being paranoid about testing is okay.
Okay.
Okay, and then also anything else that was affecting you for when doing recursion?
No, that was really it. I mean, I think it's mainly just like testing, as you can kind of see.
Mm-hmm.
But no, not that much really. I mean, I think it's mainly like what you wrote down, like pass by reference versus pass by value,
Mm-hmm.
like that part of the concept. Other than that, I think yeah, not much else that's like a red flag in my head right now.
Okay.
Yeah.
What about? And then I need to look at your. I'm gonna look at your practice diary a little bit. So you didn't write. How many are these the problems that you did? You only did 3.
Oh no, these are the problems that I failed on. Yeah.
Okay. Because it's not important. It's like not only do you need to write down the things that you didn't do that you failed
Mhm.
on, but you should also do the problems that you succeeded on and say, hey, this is what I did right. I think
Got
it's
you.
all it's important to balance it out because if you just focus on all the things you did wrong, then you're just gonna end up with only one side of the equation. Then you just might end up screwing yourself over by eliminating the things that you're doing right.
Okay.
So
I typically the entire collection of the poems I've done is like under like a folder.
okay.
But yeah, I can you how would I do that then? Like what I did right? Like I
So it
guess.
matched up with, like, what was the key to solving the problem? What insights did you have, and why did you and why were they the right? Why was the right? Why was it the right path?
Okay.
That's really it.
Okay.
So, record your victory. So I'll also say record your victory. Record your victories as well. So it's kind of important because otherwise you're gonna look at fuck. I'm fucking failing, you know.
Mm,
And then
okay.
this whole interview practice diary is gonna look like a fucking chore. It's gonna look like a record of your failure, you know. We gotta have like a little bit of success in there too, because we don't want to throw the baby out with the bathwater.
I yeah. Yeah.
Okay. Either
That's
way,
right.
we're gonna talk a little bit about like what's it called being, like I said, for you to test thoroughly, and we're paranoid about it. Good. And I think it's okay. We're gonna do next is like what constitutes good testing. I think that's the next thing for us. So
Okay.
let's actually address this right now, and before we actually go into the a problem. So let's
Okay.
take the example of a tree, right? How do I know I have good testing for a tree? Well, then I need to try all the possible ways, like in this context of recursion, right? So one way is that for every single possible combination of nodes plus parent plus child, then as long as I can test and prove all those scenarios, then I'm good. So what do I mean by this? So I mean, like, let's say we have a node with 1 child, node with 2 children, and then also with parent plus node, and then parent plus node with 1 child, parent plus node with 2 children. As soon as I can prove that my recursive code works in all 6 cases, and for all variable values that I pass in, then it's gonna be gravy, right? So let's take like a typical depth first search, right? So let's say that we have our evaluate, we have our node, and then DFS node.left, DFS node.right, right?
Yeah.
So right now, in this particular case, how many cases do I really need to test?
Right now, you just need to test like 2, right? Because you only have node.left and node.right.
I would argue that you need to test. There's 3.
Oh. Let's say node with 1 child, node with 2 children, and
the node itself with 0 children.
Node itself, yeah. Or 0 children, yeah.
Yes, because what if these DFS doesn't get executed? You know, I mean. So I would argue that in this case it's 3 because you have the evaluation of the node itself, and then you're passing it left and right. Now, if we were only going down the left side, then I'd argue, okay, well you can get away with node with 1 child, right?
Yeah.
But then let's say I have some kind of path array here, right? Now, how many are like use your imagination here? What kind of test cases do you think? How many test cases do you think we're gonna need?
With the test cases in
How many situations do you think we're gonna need?
Situations, got you. I would say it's around the same, right? I mean, the only thing that we introduced is just like this path, variable, which even though we're probably using it for something, the actual traversal itself, it still remains the same. It's like the node either has 0 children or 1 child or 2 children.
Okay, so let's say I do path output. Let me just do this then. Let's say I do this. Does that change your answer?
Yeah, but the only scenario I can think about is just, keeping track of like whatever is in path, I'd say.
I'm gonna say, I mean, yeah, technically you are right that in theory we should be able to only get away with 3 children. But the thing is that I would argue that as long as you can prove, I would say you'd have to prove it 6 ways. The reason why, like, if I was gonna demo it to someone, I'd prove it 6 ways. And my test case would be like, hey, I'm gonna test a node with a parent here just so I can prove that path works. And then whatever I'm doing with path works as well. Does that kind of make sense?
Yeah, kind of. You're just kind of saying like,
Wait, hello? I can't hear you actually.
Oh, sorry. It says can you hear me now?
Oh yeah, I can hear you.
Yeah, isn't parent plus node kind of just similar with equivalent to node with 0 children?
I mean, parent plus node and node with 1 child, arguably yes.
Okay.
But it's more just here for the sake of completeness. Yes, in theory, there are going to be things that will seem will seem redundant. But it's mostly just here for completeness because sometimes we are going for, like in this case, parent plus node. In theory, we're only looking at the node and we're coming from the parent, whereas node with 1 child, we're going from the node to the child. So it's kind of the direction. And I know I'm being a little bit ambiguous here, but it's mostly just to show you, hey, consider like what you're doing in the problem and the context of it, and then associate that with how many test cases you need, because sometimes it may or may not be relevant.
Oh, so in this scenario, we're kind of creating testers. In essence, like we're kind of drawing tree. Oh, okay. It's like kind of the same thing as like when they give examples, right? And then we're testing with examples. It's like we're doing like, oh, here's a node. Okay.
Think of it like a finite state machine. Like if I go from a parent with a node to a node with 0 children, and I can handle like all these different different ways that the problem moves around between all these different states. If I can prove that it works along all those paths, then I've proven that I've solved the problem for every single possible value.
Got you.
And this is like this is one way to think about it. Another, and it's very easy to visualize with like trees and recursion.
Okay.
So let's actually take your problem of paths summed, right? Let me actually show you how I would test it in this context. And then we'll go ahead and do a problem, and then I'll give you a chance to go at it too. Don't let this affect you too much, but I think it's a good practice. So let's say I am here, right? Given a binary tree and a number s, find up all paths from root to leaf such that the sum of all node values of a path equal to s. So I would use your let me swipe your algorithm, right? So I would say here immediately, like, okay, well, I want to test, in order for me to like start off the algorithm, I would say very easily node with 0 children. Node with 0 children, and then there's also the factor of, well, is the path 0 or not 0? Why? Because one of your factors here is that it's contingent on finding that the sum is 0, right?
Right. Yeah.
And so if the path is, or should I say sum is 0 or not 0. So actually, let's put a star here. Just to say, hey, we're permuting. Okay, well then, if I know that I can reach a node with 0 children, where the sum is 0, then that means that I can handle a leaf where we've arrived at the answer and a leaf where we have not arrived at an answer. Right?
Yeah.
Because this could be part of an overall greater traversal. So the next I would say node with 1 child, and then times the sum is 0 or not 0, right? And then I might also want to start saying, well, what about the items in the path? Path empty, non-empty. Can I make sure I record those? You know, and while it might seem a little bit pedantic to just like do this permutation over and over again, because in theory having the path empty and non-empty should not really matter. Because it's like, hey, well, I'm just going to do a path dot copy into current path, right? It's just more here to acknowledge that this exists and to acknowledge that, hey, yeah, this is another variant that I may need to handle. But then if the code to handle it is super simple, like push the current path on to it and then pop it off, then it's like, it doesn't really matter if it's empty or not. Right. Is this making sense?
Yeah, because it's like, in essence, like, whether the path is empty or not, like, in some sense, like, it matters. Well, in some sense, it's going to be non-empty, I think, right? For the
in
path.
some cases, it'll be empty. Some cases, it won't be empty. But essentially, what I'm trying to get you to do is, like, acknowledge, hey, well, these are all the variables that you're using. You need to check, you need to reasonably cover the permutations of, like, the nodes and then the values of those variables as well.
Okay.
So it's all about knowing, like, the different possible combinations that you enter into that function with. Think of it like a state, right? Yeah, let's say that we have state A, state B. Let's say alpha. Let's call it states alpha, beta, and gamma, right? And let's say alpha can take on the values A, B, C. Beta can take on D, E, F, and then gamma equal G, H, I, right? And so let's suppose they're all independent. Then you need to come up with every single possible combination of these things. So it's going to be ADG, ADH, ADI, ADE, etc., etc., etc. So how does this relate to your function, right? Well, what if it happens if, like, let's say your sum is 0, sum is not 0? That could be your alpha. That could be like state alpha, right? And then beta would probably be like the different combinations of parent-child nodes. And then gamma would be like the number of elements in the path or something like this. And all these three things are technically very different from each other, are all independent, right? In theory.
Right.
So it's like just being able to acknowledge that all these different combinations do exist. Whether or not that changes your problem, it's a different question. Like I said, if all you're doing is really just pushing onto the current path and then adding it to a master list and then popping off the temporary path whenever you need to, then it's like this state doesn't really matter. But it's acknowledging that is a factor that you need to address, and then it's like, okay, well, I don't need it because of my implementation, then eliminating it. So
I see.
And so making sure, and another way to think about this, if this is a little bit too abstract, is like look at every single possible statement here in your pseudocode, and then know what can happen if the statement is followed or not. So for instance, if like in your code here, what happens if the node is, you have this null check, right? What happens if you pass a null in? A good way to test it would then be, if I'm passing in a null into the function, then I should probably have that as one of my test cases, right?
Right.
And then you have these non-nulls as well. So then what is a subset of the non-nulls? Well, I need to push the node onto the current path. Okay, so then subtract the current sum from the node value. What happens if this current sum is 0 or non-zero? if it's equal to the node value or not equal to the node value. If what happens if we go over it or under it, you know? And so it's like all these different ways that current sum can possibly exist. So this goes back to the idea of states.
Mm-hmm.
So this is like another this is another factor that you need to test for.
Interesting.
Does it make sense?
Yeah, it definitely makes sense. Would you say like this level of thinking is almost like, for lack of a better term, like micro, like managing low key, like in the sense of like testing per se?
A little bit. I'm not gonna lie. Like I'm giving you the basics. I'm giving you like every single little detail that you need to understand. And then after that, with some time that passes, you will understand and you get the practice. You'll understand which factors are necessary and not necessary. Everything I'm describing to you, I immediately do within like 10 seconds. It might take you 5 minutes the first time around, but after you get the hang of it, you start understanding. Hey, yeah, I can do this in 10 seconds. But I'm giving you the basics right now.
No, makes sense. Yeah. Because no, I think I never thought of it in the sense of like alpha, beta, gamma, like these different states. But I think once you explain it, yeah, definitely.
Yeah, because sometimes that's a little bit too abstract for some people. So usually I like to describe it in the way of like a think of it like code coverage, right? Like a typical code coverage tool is going to look at every single line and see if you are testing for the values that those lines can take on. You're doing it essentially the exact same thing.
Mm-hmm.
It's just that I'm kind of giving it to you at like a high level that a computer checker is not going to necessarily be able to understand abstractly. And then also like if you look at line by line, then you should be able to test it. But also you should have some intuition of how you need to test it going into the problem as well. It might not be complete, but because there's some implementations that you need to check as well. But if you have if you can go into a problem and have an 80% idea of what you need to test and cover, I think that's pretty good.
Okay. Yeah.
Okay. So if that makes sense, we can actually do a problem.
Sure. Let's do it.
Yeah. Let me pull up a problem. And we're going to do another recursion one because I want you to try this idea out. Have we done? I think we did lowest common ancestor, right?
I think we did lowest common ancestor. Wait, let me double check. I feel like we've done before, but to be quite honest with you, I always forget how to do it.
Okay, if you forget how to do it, don't look.
Okay.
I see we've done it before, but
Okay.
I want you to apply this idea as well.
Okay.
If you forgot how to do it, that's perfect because then I can give it to you again.
Yeah, yeah, fuck.
No, that works for our benefit. It means like we can drill the exact same issues.
Right.
So let me bust out the timer. And don't worry too much about the time since we're trying a new idea right now.
Okay.
But I'm just gonna do it just for the sake of doing it, just in case there's other things I can cover. So
Sure.
let's go. So given a binary tree, find the lowest common ancestor of two nodes in the given tree, right? So for instance, let's say I gave you 6 and 7, right? The lowest common ancestor of this would be 5.
6 and 7, those, yeah.
Okay.
Yep.
There you go. Have at it.
Sure. Yeah, so since we have a tree, it's like I definitely know that it's going to be like a DFS kind of implementation or pattern.
It can also be BFS, so I wouldn't be so hasty to declare that.
Oh, what'd you say?
I wouldn't be so hasty to declare that because it can always be BFS as well.
Oh, okay, yeah.
Because you're just kind of like throwing it out there. It's like a little bit risky, but it's just a side note I thought I'd make because I don't want you to commit yourself just because you say it, and that's a pretty high risk thing. Like you say, oh, I'm gonna use DFS. Well, because you said it now, you're kind of committing yourself to it.
No, that's fair. So yeah, let's just say for the it can either be DFS or BFS. The reason I think going with DFS is a better solution is because I think with BFS the way kind of it works is that we're going like level by level, and in terms of keeping track of the relationship between the parent and child, it's harder to do with BFS as opposed to DFS. Whereas with DFS, we can go from, we have like access to the nodes left and right child. And in the case of this problem, when we're trying to find like the ancestor of two given nodes, like that kind of works in our favor. So yeah, just from kind of thinking from that point, I'm gonna go with DFS.
Okay.
Um,
I wouldn't say level
that
by level as well. I would think it's like in order, post order, pre order, traversal. But okay. Again, this is me being nitpicky, but we'll talk more about it later.
sure, sure. Okay. Um, with DFS, and to kind of do this, let me think. Oh, fuck! Come on, come on.
Just remember,
DFS.
walk through knife solution. Try to get a solution first, and then improve it.
Okay. Yeah. So with DFS, like, there's what else can we do other than just like traverse using DFS? We have doing the left and right child. I guess the naive solution first would just to be like, for each path that we go down, we store all the nodes that we encounter. And after that happens, essentially like from each of until we reach like, let's say, the 2 given nodes, right? So DFS until reaching node 1 and node 2. And the minute we kind of do this, like the central idea is like, I guess from a naive perspective is like, when we're doing like node 1, right? And we like, since we're using DFS, until we reach it, we're like storing every node in the path, right?
Okay.
And then when we do like, when we're on our way to like node 2, like we do something like pretty much similar, but like, let me think. So let's just say we're doing the same thing for node 2. And since we have access to all of the nodes that we store, the first ones that we come across when we're going like, let's say reverse order. So an example for when we go to 1 is like 3. Or sorry, like the example you kind of just gave, right? Like lowest common ancestor of like 6 and 7, let's say 3, 5, 6.
Okay.
We are storing that in the path, and then let's do 3, 5, 2, 7, right? We found both of the nodes, and 3, 5, 6, 7, and all we have to do essentially is like depending on which one, I guess this is me trying to like kind of optimize, but depending on which one is like at a greater depth, like we can basically just like start from there, because we know that if it's at a greater depth, essentially the lowest common ancestor would does it really matter actually?
I mean, you have an answer. Well, let's acknowledge that, but I think you also understand that this may not be the most efficient as well.
Yeah, because right now I think like but the essential kind of like, I guess, naive solution is like we store the path for each one of the nodes, pick one of the nodes, work backwards, and at the first occurrence of, like, let's say we go from 7 to 2, right? 2's not in the other array. We move on. Oh, 5's here, right? We see 5, and it's just like, oh, 5's here. That's
why not? Okay, well, why not just go scan from left to right then and find the last element then?
Oh, right to left?
Left to right.
Left to right, and find the
last common element, yeah.
Last common element. Yeah, I guess that could work too. So it'd be like 3, 5. Yeah, actually.
Yeah, well, I don't know why you make it so complicated, but anyway. I'm not gonna. It's again smallest thing. All right, so you don't understand. You understand that is not the most efficient thing to do. So then my question now is, okay, well, what's wrong with it? Why is it not efficient?
I think honestly, what's kind of not efficient about it is like I would have to traverse like all the way, like down to like whatever. I would have to store all of these nodes, right? But not only that, it's like that takes time to like process. I think. I don't know. It just seems a little like I can't give you like a straight answer other than just like it feels that storing each path just seems like a little excessive.
Okay. Well, how about this? Give it to me in terms of time-space complexity.
Yeah. For sure. So in terms of for time-space complexity, so for the time to find like each one of these nodes, like to find node 1, it would determine on like the height, right, that we're traversing for each path. So that'd be like, I think, O of H, actually, I think, for time.
For the time? So can you turn off your phone?
Sorry. Yeah, let me... So sorry about that. Give me a sec.
Okay.
Sorry. For the time, essentially, like, assuming we're traversing all of the nodes to find, like, whatever the nodes might be, I believe time would be O of N. And the space would be the height of each one of these nodes that we're storing in.
Okay, sure. So
would...
time, yeah, that's fair. So
yeah,
I would be more accurate and say order 2n because you're traversing it twice to find path node 1, path node 2.
correct.
Okay,
yeah.
So then, so you are using extra time and extra space. So I mean, there is obviously. So then, can we do it so that way we're not using extra space, or possibly lower the time?
Yeah. And I think that's where I was thinking about, like, using the depth kind of stuff. But again, I don't think that's the right one either, because just kind of looking at, like, the paths here, like, depending on if we go with node 2 or node 1, right? Or in this case, the longer path versus shorter path, like, the difference seems to be almost insignificant. If I use the depth, let me think.
Okay.
So find one path and the second path.
Okay, so remember what I said. There's something in the naive solution that's working. The question is, what is causing you to have this inefficiency, and how can you eliminate it? So I want you to ask yourself those questions.
Okay. So what is causing inefficiency? I think perhaps like the storing is causing no. Traversing the tree like twice perhaps is causing
That's
inefficiency.
also one. And also storing is causing it as well.
Yeah. I think storing is the most obvious.
Okay.
And so if storing it is causing the inefficiency, then how can we eliminate that kind of that inefficiency? So right now, why am I storing it? Well, I'm storing it because I need to keep track of all the nodes that I've traversed to that node, such that I can find some kind of commonality between the two paths, right?
Yes. That's
the main thing what I'm doing right now. But how can I essentially perhaps not have to? How can I able to achieve that same thing without having to store the paths is right now?
Correct. How do you achieve that? How do you find the commonality without actually storing the path to that node?
Right.
So you're asking the right question. Yes.
Yeah. So I guess first off, maybe there's some way to maybe only store one path, and then like based off of that, like
so you're still storing paths in that case, though.
I see. Yeah, you're right. So okay, how can I is there some kind of
There's no magic bullets.
Okay, yeah,
Remember, no magic bullets.
God damn it. Yeah. Okay.
Don't think in terms of magic bullets. There's never a magic bullet.
Okay. Yeah.
So you've kind of eliminated that you cannot use like the path there because it otherwise requires storing it.
Mm-hmm.
So what's your other option?
If I can't use the path, God damn it. Can't use the path. Okay, come on. If I can't use the path, right? Okay, what else can I rely on? If I can't store the path, what else can I rely on? I need to find something that's common between both of them, and that's what I return.
Okay, let me help you out a little bit. What makes 5 the answer, but not 2 or 3?
What makes 5 the answer, but not 2?
Yes, if I gave you node 6 and 7, right?
Mm-hmm.
So let's say node 6, node 7. Why is 5 the answer, but not 2 or 3?
Because that's the one that's the node that it satisfies 2 conditions essentially.
Okay.
It's the closest to 6 and 7, and it's also the direct, like, it's an answer. It's the closest to both 6 and 7, but also it fulfills the condition that it's above like 6 and 7. If that makes sense.
Okay, sure, it's above 6 and 7, but 3 is above 6 and 7 as well.
Right. Well, there is 5 has like it's closer in like depth than 3.
Okay. So what is it about closer in depth that makes it better?
So 3 is like a common ancestor of 6 and 7, but
Yes.
it's not the lowest.
Yeah, of course, but that's like going in circles now because I'm literally asking you to tell me what the lowest common ancestor and why is it the lowest common ancestor?
Why is it the lowest?
Yes.
Yeah. Well, you can get to, so if we look at just 6 and 7, right? 2 is above 7, but 2 is not an ancestor of 6.
Okay.
You can get to 5 from 7,
Mm-hmm.
and 5 is the ancestor of 6, so therefore 5 is the lowest common ancestor.
Right. Okay. So which means
Yeah.
that you found 6 and 7 as children of 5.
Correct.
But and 3 is also 6 and 7 are also children of 3 or descendants of 3.
Yes.
So then what makes 5 the answer but not 3 using that statement of fact? I'll give you another minute and then I'll point it out to you and it'll be pretty obvious.
Okay. Fuck. Fuck.
Okay, okay, fine. I'll give it to you. 6 and 7 are in the left subtree and right subtree of 5.
Okay. Yeah.
They're direct, like you can find 6 in the one of the subtree in the left subtree, and then 5 and then 7 in the right subtree of 5. But you can only find on one side of 3.
Yeah.
And notice there I did not use anything other than the properties of the tree. I didn't try doing any crazy shit there. All I noticed was that 5 and the 6 and 7 were like on 2 separate sides.
Right. Yeah. No, that's correct. But how does that? Right. In this situation, you're right. Like it's 6 is on the left, 7 is on the right. Whereas for 3, 6 and 7 are both on the left. Um. Oh wait. So are you saying that like another way to approach this problem, or maybe a more optimal solution is um, we run like, let's say, DFS on the left side of the tree, right? And depending on where we find like an occurrence of like both 6 and 7, right?
Mm-hmm.
Since by the nature of how we're running DFS, right? So it goes from 3 to 5 and then 5 to 6. So that's one.
I
We go
think
back to
you're
five.
still hung up on this idea of paths.
Okay. No, I'm just saying like because we know that like it's now in the left subtree, we don't have to go to like the right subtree, right? Or maybe I'm
Well,
overcomplicating
you're
that.
overcomplicating it. Start over.
Ah, fuck.
I
Okay.
told you I told you a fact that you have one node in one subtree and one node in the other subtree. That is your condition for finding the lowest common ancestor. And you're talking to me about DFS.
Yeah. Um,
So my question to you is, can you construct an answer knowing that you know using that condition?
uh, yeah. So if we kind of think about it, right? If we found 6, right? Let's say, like kind of using your condition, right? Like we know 5, or let's just say we know that it has to remain on the left subtree. Like one node is on the left subtree, one node is on the right subtree.
Mm-hmm.
Then the minute we find like a, in the minute we determine that whatever node we're on, its left child or right child is one of the nodes,
Okay.
then we can just basically say like that node is the lowest common ancestor, right?
Yeah.
Yeah.
So then why don't you write me a function that does that?
Okay.
Or write some pseudocode, either way.
Yeah. So, am I still allowed to use DFS or?
You can, but I get the feeling you're gonna be hung up on it. But yeah, if it helps
Okay.
you solve the problem,
Sure,
you're
sure.
free to use it. I just
Sure,
don't
sure.
want you to like marry yourself to whatever preconceived notions you have. I want you to be a little bit more flexible on this.
Okay. Yeah. So essentially, it's like we're traversing like the tree, right? And um, traversing yeah, let's just say traverse tree. At each node, um, check if node left or node right
Mm-hmm.
is one of the two nodes,
Okay.
right? If the above, if it is, right,
Okay.
and we basically know that that is the lowest common ancestor.
Okay.
Yeah. And then we just return that node.
But what if it's in the case of 7? You know, like it's not 6 and 2. You know, it's not gonna be their direct child. So how do you want to handle that?
So, depending on where we found the, uh, depending on, I guess, like whichever one, and this might be me overcomplicating a little bit, but let's say we found like node.6, like we're at 5 right now, right? And at 5, we have access to 6, which is one of the nodes. We would just only target like the nodes on, I guess, the right-hand side
Okay.
of 5, to find if 7 is there. And if we find it, then like 5 is basically the lowest common ancestor. But I feel like that solutions can be like flawed just because like let's say 7 didn't exist there, like 7 existed under 1 or something like that.
Okay. I mean, so then what is it that your function needs to actually return then? Let me ask that.
What the function needs to return, I think, is basically like true, like a Boolean.
Okay.
I'd say, yeah. Because in this case, we don't have to determine whether or not, like, we just need to make sure it exists in that right subtree, right? Like for this example. So if we found 6, we basically go through the right subtree, and if we find 7, then 5 is going to be the lowest common ancestor. But if we don't find it, then we know that, all right, like 5 is not, and then we would go up till 3, and then we traverse the right subtree for that.
Mm-hmm.
And like, or like for whatever 3 is, like, and then once we find 7, then that means like 3 is going to be the lowest common ancestor.
Okay. Okay. So what I'm asking is, your function. You say you want to return a Boolean, right? What does that Boolean represent?
If the node exists in that subtree, but more importantly, if that node is the lowest common ancestor or not.
Mm-hmm. Yeah. Okay, sure. So you're basically asking to see if it's in the subtree, right?
Right.
So then what's your algorithm going to look like then? You say a check if node left or node right is one of the 2 nodes, which is, that's not necessarily correct. So then let's find something that would actually work.
Okay, yeah. God damn, took me. Okay, so traverse each subtree, at each node, find out if it's one of this subtree. I guess basically, right, like at each node, right, if we have like, a function, like at each node, if we just recursively call function, at each node, right?
Mm-hmm.
If node.val is node 1 or node 2, we return like true, right?
Okay. Because your Boolean represents if you found one of the nodes.
Yeah.
Okay.
So then we return true. So that's kind of just like the situation. Like else, we basically like I'm just going to use like call like function node dot left.
Okay.
Function node dot right.
Okay.
And so let me just kind of run through real fast. So we're going, so at each node, let's just say 3. 3 is not node 1 or node 2. So we do function left, function right on 1. And so we're going to 5. 5 is not node 1 or node 2. So then we go into function left. And then 6 is, so then we return true for node.left. And then we go into the right side. And we have 2. 2 is not 7, 4. But once we hit 7, we return true. So then it percolates kind of like back up. So, yeah.
Okay, so remember your condition. Now you have a function that says, hey, is one of the values in my left subtree, is one of the values in the right subtree? Now, how do you make use of these results then?
Yeah, so in order for something to be like a lowest common ancestor, both node left and node right have to return like true, right? That's one of the conditions. So maybe something like return function node.left and function node.right to kind of account for that.
Rephrase that for me. Keep it a little bit simpler, because I think you're kind of you're starting to jump the gun a little bit. What does this represent?
This represents the first line represents traversing the left subtree, and then the second one represents like traversing the right subtree to find the nodes. And if it finds it, then this will return true.
Okay.
For each one of these function calls.
Sure.
Yeah.
Sure. And so you need to basically, and so you said you need to find an and of those, right?
Yeah.
Okay.
Because essentially, like, for one of the cases, like let's say 5, right? In five's case, when we're doing node.left, that would return like immediately after like one kind of like recursive stack down.
Okay.
But for the function node.right, that's going to take like a little more time to do. But I'm this is going to sound funny, but like it's I hope it's going to return back up like true, such that we can tell that it exists within there.
Yeah, you hope, you know. But that's like, you know, like I said, it's you're wishing here. Okay, so at least write that in. So for now, let's accept that as like the tentative solution for now, returning and. But you already understood that, hell, wait, I need to find a way to return this to my original function, because otherwise I'm going to get hit with a false. You understand that at least. So then, how do you want to store that? Let me ask that.
How do I want to store the Boolean values, right?
Well, okay. No. You said that you said earlier that if you have 5 as your answer.
Yeah.
But, you know, you need to be able to pass that back up to our function or whatever our original calling to be, hey, yeah, 5 is our answer. Because if I rewound the stack, I'd go back to 3 and I'd lose that answer.
Right.
So how do you want to save the answer?
Couldn't we just set like, and this is it possible to set like some kind of like variable, like like a flag or something like that?
Yeah, I think that's fair. I mean, why can't you?
Yeah, like some kind of flag that indicates like, you know, we found like the common ancestor or not, and that flag not only contains like, it serves more than just like a flag. It just like it serves the actual like ancestor.
Sure. You could just say answer equals if function, you know, left and right is answer, then return then mark the answer. You know, I'm fine with that.
Yeah. So like, so we have like, LCA, and it would just be like the LCA, for lack of a better term.
Sure, I'm fine.
Yeah, and so like, and that would just basically be said, I think, like in this condition returns, both of these returns correctly. So if it's a set here, found CA is equal to node. Yeah.
Okay, so you found it, fine. And then you need to have some default value. Okay, so now let's pivot to the idea that we had before of testing, right?
Mm-hmm.
How do you want to test this function?
Well, traditionally, I would just run it through like some tree examples, right?
Sure. Let's apply this idea of being stateful, though.
Stateful. Okay. I'm just gonna scroll up real quick. Yeah. So stateful. So we kind of have like the 6 scenarios, which is node with 0 children, node with 1 child,
sure,
node with 2 children. So let's start off with those 3 conditions first.
Okay. What else do you have to worry about as well?
Also have to worry about whatever the ancestor is supposed to be, right?
Try again.
I'm not too sure.
Yeah. What about node 1, node 2? These are variables that you're injecting in here.
Yeah, the show we're supposed to return. Yeah. Or like fine. Yeah.
Okay, so then what are the other ways that you are going to test this? Okay. How are you going to test this part as well?
Yeah, so I think kind of for this might deviate from like the state thing, but essentially it's just like we have an idea of what node, or we know what node 1 and node 2 is supposed to be. We also know what like LCA is supposed to be. And I would just probably give it, I don't know, I would just typically run like a tree through it, right? like knowing these kind of things.
Okay, well, yeah, you could run a tree, but keep in mind, node 1, node 2 is going to be your killer, actually, I would argue. So why do you think that might be?
Uh, I actually don't. I'm not sure actually.
Well, I gave you the possible scenario of 6 and 7, right?
Yeah.
Where none of these are going to be ancestors of each other. What happens if I give you 5 and 7?
Oh, okay. Yeah.
So when I say stateful, I literally mean every single possible permutation.
Oh, okay.
So what are the different possible permutations of this? So not only do you have like the parent-child stuff, you also have the relationships of node 1 and node 2 with each other. That's why this is important.
Fuck. Yeah. Okay. Yeah.
Okay?
Yeah. No, you're absolutely right on that one.
Okay, so now that you know, does that change how you're going to approach the problem?
I think so because it's like it stops short, right? It's not going to. The function call is essentially going to end at like return true. Let's say in the 5 and 7 example. So, I have to think about a way that addresses that condition in which we find like one node, right? But we don't like lose this path.
Correct.
To go down or lose this tree all entirely for this return true. Because what's going to happen is we're going to traverse the tree. We're going to go to node.val is like 5, and it sees that it's either node 1 or node 2, and it's going to return true. And it's going to go back up essentially and return that, and then 3 is going to call there without kind of going down. Okay, so
yeah, how are you going to adjust your algorithm? How are you going to adjust your function in order to accommodate this essentially new idea? What does your condition now become? It's no longer is it left subtree or right subtree. What is your new condition?
it's no longer the left subtree or the right subtree. It's now.
What do you think the solution actually is?
Fuck, I keep going back to paths like in my head.
Yeah, I knew this was gonna be a problem. I think I called it out earlier.
Yeah, because I keep thinking like, oh, let's just put this into like a path then, or like.
I mean, all you were doing is just massaging a function, an answer that kind of works, and we're just saying, okay, let's add a few more layers and a few more things to make it actually work.
Yeah. Shit. So it doesn't become left subtree or right subtree anymore. Fuck. Let's see. So if it's not going to be the left subtree and right subtree in this case it's essentially just 5 twos. What if we just put like
no magic bullets. Seriously, I'm gonna fucking yell at you if you think of some magic random ass bullet.
Okay, fair enough. Let me.
Just think of it holistically about the problem. Just think of it in terms of what I just told you. You now have a new material fact. How do you accommodate that in your code?
Well, rather than return true, we would want to like just keep going.
Well, okay, sure. Let's do this by examples. What happens if 5 and 7 are the nodes I give you?
Right, so it would encounter 5 first.
Okay.
And it would return, like, it would go up because it thinks that the code right now is written in such a way that it thinks that there's no other information there, in the sense of like, oh, I found the left subtree, right, of where it is. So how can we massage that into it not thinking it's the left subtree. Could it just be as simple as like, rather than return true, like 5 is just a possible like lowest common ancestor?
5 could be a possible lowest common ancestor, but how are you going to prove it?
Essentially, like we would just keep iterating on 5 itself, and if the other node is found within like 5's left subtree or just below 5, then 5 would be the lowest common ancestor.
Okay, so which means that you are evaluating, you know for sure you have to evaluate the node.
Yeah.
But that also means that you don't know, you just evaluating the node by itself is not the whole picture. You have to do other shit as well.
Yeah.
So why don't you try to run with that idea?
Yeah, so rather than just returning true, right? Well, why is 5 like an ancestor, right? Well,
Why is 5 an ancestor? Because when you get into that node, you don't know it just yet. So what more do you have to do?
We have to determine whether or not like 5 has more information below it. And I think the way we can think about in that approach is like, hey, does 5 have any children?
Okay.
So if we think about it like this, like if node.value is 1 or 2, maybe like introduce in pseudocode, like
I'll get rid of their here you go.
Yeah, like is node leaf, and if it is, then we return true, but otherwise, like if not, function like node.left, and or node.right.
Okay, I get what you're trying to do here. If you find one of the nodes in the left subtree or right subtree, okay.
Yeah, so that would kind of address that condition where it's when the first node we find isn't a leaf node, and it is also one of our node 1 and node 2. Yeah.
Okay.
Yeah.
And then let's complete the thought. If the node is not a leaf and you find something inside the left subtree or the right subtree, what are you gonna do?
Yeah, so if this returns, and this is getting a little convoluted, I acknowledge that, but
It's fine. We can always iron out later, but we want to get our ideas down first.
Yeah. So essentially, if this returns like since it's an OR statement, right? If it finds it in its left or right subtree, then that means then whatever node that we just kind of like was like here that came in here is the lowest common ancestor.
Okay, that's fine. So then how do you want to express that?
So it is kind of like the same format as like what here has, but essentially it's just like if that is the case, then like found LCA would just be that node right there. Yeah,
I think that's fair.
Yeah.
Okay. I think okay. So, but yeah, like you said, it's a little bit messy right now, but at least you have something.
Right.
Okay. Now let's clean this up because obviously the code is not complete. It's not nice. Let's clean up this idea.
Yeah. So let me just. Fuck. That was just. Oh my god, dude. Oh fuck me.
It wasn't that hard, right?
Yeah. Fuck.
All you really had to do was just step through the damn thing.
Yeah, the fucking path shit, bro. Oh my god. What the fuck this? No, sorry.
It's not. It's fine. Swear as much as you want. Get it all out. Get all the frustration here. It's okay, man.
All right. So to kind of just clean this up, let's see. Right now, what really kind of needs cleaning, I think, is just these, like, I guess these two conditions.
Okay, sure.
And so I guess to clean it up, I would kind of do the testing that kind of, or like the permutations.
Sure.
So let's say for original example, like 6.
I would still write out, keep in mind, I would write out the tests. So what exactly are you testing?
Okay, yeah. So testing. When we do, let's say node we're just doing node 1 is well, I think, yeah, node 1 is 6, um, node 2 is 7. So we start off with node is equal to 3, right? And we know that the node value is not node 1 or node 2, so the first if condition doesn't get ran. And so we move on to node, we first call like node dot left, right? If node dot left and node dot right. So we go into node 5, and we see that 5 is not node 1 or node 2. And then so we go into 5's node dot left, which is node 6.
Okay.
And
keep in mind, I want to be like you're saying you're node 3, node 5, node 6. I would try to separate your function call stack as well. I get what you're doing. You're basically doing the traversal through it. We'll talk a little bit more about this later, but I want you to be a little bit more atomic about this. Like, for instance, what step are you at? Yeah, I get you're trying to simulate the function call stack, but because once you go deep into the stack, you kind of and you pop out, you kind of need to remember what step you're at, just because that information does get lost. So I want you to at least write that down.
Okay. Would it be too much overkill to just to also be like, oh, node 6 is the child, or like I guess I kind of know that already.
I mean, you could say it, but then you don't necessarily need to write it out. Okay. It's like slow and smooth first, then you can get faster later.
Okay. Yeah. So we know that we see that node 6 is like node 1 or node 2.
Okay.
And we also see that it's a leaf.
Okay.
Right. So this would just be return true.
Okay.
So we pop back and then we say like if true, and like now we call it on node dot right.
Okay.
And so now we go into 5, and then for node dot right it's node 2. That's neither 1 or 2, so we do a function on node dot left.
Okay. Personally, I would annotate it as node dot left. Dot left, just to say, hey, this is a step I'm on, but.
Okay.
But yeah,
gotcha.
Some kind of flag, something that will tell, that will remind you, hey, this is the step you're on. Some way to really do that for yourself. So okay.
Gotcha. Okay. Yeah, and this goes into node 7, and yeah, 7 is what we want. Node 2. So then basically, node dot left is equal to and oh yes, for that it's a leaf, right? So that's also something else to keep in mind. Node 2. So this was node dot left, and then it returned true, and then if we run it, so right now it's if true function node dot right.
I mean, you can go through it, but I think we know the answer to that one.
Yeah. So this one is this is just basically overall it's going to be false.
Okay. Right? But you did find one of the nodes, though. So how do you want to relay that information?
Yeah. So kind of knowing that, I guess. Oh shit! I deleted too fast. Let's see.
Yeah.
So, we know that this is going to be false, right? But we want to relay to node 5 that it's actually going to be true. Is it as simple as just doing or? I don't think so. Function no. Well, let me just see real fast, actually. No, I think we need to have like this and condition here for it to be.
Okay, so you do need an and condition in order to mark it as an answer. That's true. But
yeah.
The thing is that you've only found one of the nodes. You didn't find 7 as the answer. So then what do you need to do?
So we kind of, in terms of marking, right? I think my mind immediately jumps to like how can I set something that is what do I need to do? I could just like indicate that node has been found.
And your function is defined as if we found something in the subtree. correct?
Correct.
So what do you need to do?
Perhaps like I know we have something called like found LCA here.
Okay.
But maybe we can just have something like found node.
Well, isn't that just what the return value is?
Right.
By definition, you've already declared that your function is going to return true or false if we found something in the subtree.
Right.
So how do you return that? What is the statement or condition that you're going to use in order to express this idea?
Something is true. So right now this is not working because I'm doing this and thing here.
Well, you're doing and to assign an answer. So what else do you need to do?
Can I just do like left and like right? So, let's say,
Instead of overcomplicated, why not just return or?
yeah, yeah,
Because by definition, your function, you said your function is going to return if a node is found in the left subtree or right subtree, right?
correct, yeah, yeah.
So it's tautological. Like you've already said this. And I don't know if you forgot, in which case you need to write it down. But it's
yeah,
like
I think I forgot.
yeah. Then you're gonna need to write that down. Write that shit down, man.
Okay.
Every single statement of fact, write it down.
Okay. Yeah. Return. Yeah. Yeah. Okay.
Okay.
So yeah, if that's the case, then let me go back. So if true, right? Since we do the function know that right, and we return back from it, to go into here, right? We kind of call this function know that right? A function know that shit. I'm blanking. Give me a sec.
Okay. Do you need like 5 minutes to break?
No. I can push through.
Okay.
Just,
We still have another 45 minutes, so if you need the break, I would say take it now. But
no. Let
okay,
me push.
if you're good, then let's keep going.
Yeah. So if true and false, right? So we were here.
Yep.
If true and right now the function returned false, we know that the found LCA is not the node.
Okay.
Right? So now we return the function left or function right, which I guess we already have the values for actually. So essentially what this would return is true, right?
Correct.
And so this now just becomes true.
Correct.
And so if that gets satisfied, right? If true is true, now we can, based off of what's written and found, LCA is equal to node.
Okay.
5. And we could like it would return back and stuff like that, but since this is kind of like the global like variable, like we don't have to worry too much about about kind of keeping track of this since we already set it actually. So once we return back all the way here, the found LCA is going to be 5. So that's one thing. And now let's test the condition for 5 and 7. And so
the thing is that you've already found the answer though. So yeah, okay. So you're starting on something else that's new. Okay, fine.
Yeah, because my rationale is like the minute since we already know what this is going to be set to.
Yep.
Right. Since it's global, like we don't really care about like everything else now.
Okay, so then what do you want? But then it's like if you don't care about anything else, then you might want to return and not do extra work, right?
Yeah. Fuck.
So
yeah.
what do you want to do?
Honestly, like if we can just I guess return, just put a return there, I guess.
Yeah, but then return true or false.
Yeah, return true.
Why?
Um, because it's like we found it, right? Like, oh,
What by definition you return function if found left subtree or right subtree. So, I mean, technically you could return true. I'm not against it.
yeah.
But it's like I wanted you to really think about it. Like, well, by definition, you said your your function is going to do this, right? So, I mean, technically it satisfies that condition, but it's like it's also kind of a useless operation as well. So, well, whatever, you know.
Okay.
I really wanted you to think in terms of that. So, all right, I'll fill it out and then go ahead and test your other thing.
Yeah. I guess the reason why I wouldn't put false is like, if we already found it, it's like, it feels like weird.
Okay, I mean either or, true or false. I just wanted you to justify within the context of what you've defined.
Okay.
That's really the point here.
Okay, so I would say return true because like return if a node is found in the left subtree or right subtree, and in this case, since both the left subtree and right subtree like the nodes were found, that's why we would return true. Because like, yeah, like in the context of it, I guess it's kind of like a shitty explanation. I agree, but
yeah, I'll make you do it later, but yeah, just keep going. Today we're trying to test. I'm trying to get you the idea. Test this stuff. So.
Okay. And then node 5, right? So let's start off again with node 3. Node 3 is, we would just say, wait, why is this highlighting again?
Okay, that's me.
Okay. Node 3, node value is not, so this doesn't get called, so we're just going to do an if function node dot left, and we go into the left one now, and so node 5 is node 1 or node 2. Is it a leaf? No, so we don't return true. So then function node left or node right. So let's just do function node dot left again, and I guess just so I keep track of it, I'm just gonna do and, yeah, to kind of distinguish between those.
Okay.
And so now we're going to 5.
Okay, so you're 5. So you did find the value. Sure, is leap. Okay.
Yeah. So yeah, it's like for node 5, it's like I entered this condition.
Sure.
And then node 6. So node 6, it's none of these.
Mm-hmm.
So as a result, it would go into here. Oh, no. Dude, what am I saying? It would go first to this condition if node dot left, so 6. Node dot left.
Mm-hmm.
We see that's like none. So I guess at this place we can kind of just node is like none.
Mm-hmm.
Just like return false or return yeah, return false.
Mm-hmm.
Because we haven't found like node 1, node 2, so why would we return true? Yeah. So this is going to be false.
Okay.
Yeah.
Sure.
False, and now we're going to be going into function node dot right, which is false as well. So if false and false. And so this we know that it's false now.
Great. Okay.
And basically we go into function node dot right.
Mm-hmm.
And you see it's node 2.
Mm-hmm.
And again, node 2, not node 1 or node 2, since we're trying to find 7. And then we basically just call function node dot left, and this is the end. And sick, we found a node 7, and it is a leaf node, and we want to return true. So basically if true, and then we do since and function root for 2 is going to be it's just going to be false, right? So this condition doesn't get ran,
Sure.
right? Found empty, like, so this doesn't get returned true. However, since we have this condition that was thoughtfully provided,
Okay.
this returns essentially true, right?
Okay.
This whole
Sure.
node 2 thing.
Sure.
So this returns true. And so as a result, here is going to be true.
Okay.
Let me just clean this up real quick.
Go ahead.
So false and true, and this, since this was getting called by node 5.
Wait. Hold up. You're at false and true. You're at this line, right?
Yeah.
So then I want you. What else do you need to do?
Oh, fuck me. Okay, yeah.
Yeah. It's right there.
Yeah. Oh my god.
It's like it's literally the pseudocode's right there, man.
Yeah. Fair enough. So yeah, found LCA. Found LCA equals to 5. Yeah. Same thing.
Okay.
I guess.
And then also thing is that what else do you need to do?
Found LCA equals to node return.
Yeah, it might be a good idea so you're not like doing extra traversals.
Yeah.
Right.
So this would just be
Okay, I'm gonna put a stop here for this problem because I think you figured it out. I think this pretty much looks pretty good, but yeah, how'd you feel about doing this problem?
I honestly feel I should have gotten it faster. I don't think I should have. You were very generous with your hints.
Yes.
Yeah, very generous. I think overall though, in terms of testing, at least, like I was, the parts that I stumbled on was, I think, here, honestly, because like
what's here? The
return function, because
yes.
Like I think this part was actually crucial, like, and it's not even because like this stuff wasn't important. I feel like this stuff I could have, like, it was just me talking out and I was able to like understand it, right? But it just came up to when it was communicating the ideas up, right? Like that's immediately where I was like I don't know, I just feel like this was a crucial part that I failed to put down, and I think it comes back to kind of like what you said, like what is this function actually supposed to be doing? So I think that otherwise, I think in terms of testing, it was okay.
I mean, yeah, I'll jump in here. But yeah, basically I'm trying to introduce this idea of like, hey, you need to test all these different ideas and states, and you kind of missed out on the node 1, node 2 stuff. And so I was generous with your hints because I wanted you to really practice this idea of testing. So let's go through all my notes here, right? So first things first, I wanted you to be more autonomous about your description. The fact that you married yourself to DFS so early on, I think contributed to a lot of your choking, actually. Because I told you be very careful about that. And it kind of bites you later on at like around here. You're getting really hung up on DFS. Remember how you said, oh, my mind goes back to paths? I'm really trying to disabuse you of like, hey, just because it works for a pattern doesn't mean it's like, it looks like it works, doesn't mean it's gonna actually work when you actually go into the details. You know, devil's in the details and all that shit. So I was okay with you coming up with a naive solution with the pass. I'm fine with that. That's perfectly great. But the thing is that I want you to acknowledge, at least you acknowledge the naive solution, but I want you to really like say why it is ineffective or not not efficient. Because remember what you said before? You said, hey, I feel like this is inefficient. Well, engineering is not based on feeling. We don't construct software on feelings. We construct software based on like what objectively works and doesn't. You know, bugs don't give a shit if you're having a good day or a bad day. They just listen to the code, you know?
Yeah.
So, in other words, you need to be very objective about this. You need to think like, okay, well, what is right about the solution? What is wrong about the solution? What is good about it? What is bad about it? And you need to keep what's good and what's bad and so on and so forth. And so when we got to the path, you realized, hey, yeah, I needed to be able to trim out the paths, but then storing all these paths is what's causing me grief. And then my question was, okay, well, you cannot store paths. So what is the other way that you can actually identify lowest common ancestors? And I tried telling you, okay, what's the difference between 5 and 2, 5 and 3? And if I gave you 6 and 7. If you just looked at the child relationships instead of the path it takes to get to the child, I think you would have figured it out.
Yeah.
It's like I was trying to gear you in that direction. So
Yeah.
that's the first thing. Is like you got really hung up on your ideas. Like super hung up. And it's not normal.
Mhm.
You can be wrong. So that's the first thing. And so the next one would be trying to get you to work through this pseudocode. So you remember how you came up with the initial one, right? And it's like, oh yeah, well this is fine. But then I said, okay, well now that you test it, you see the relationship between nodes 1 and 2, right? What if one of the nodes is the ancestor, correct?
Correct.
Then you realized, oh shit, my code doesn't actually work because what if one of the nodes is the ancestor? And so this is like, yeah. So this kind of goes back to, okay, make sure you understand what exactly you're passing in. Because it's not just like, oh, I tested all the parent-child relationships and that's it. No, what else are you adding in there? Remember how I said before in the path stuff? Like, what are the other variables that you're passing in? Well, this is a great example of that, is that you needed to keep track of like the value of the nodes and their relationships with one another.
Right.
Yeah.
Yeah, I think. Would you say like that just kind of comes from like, I guess I know it comes with practice, but like notice like that kind of understanding I feel like comes from I guess generating like examples, correct? Like, for lack of a better term, like kind of what you highlight, like go up, like if node is scroll down a little. Like if node 1 or node 2, like that kind of relationship. Would you say like that thing is you just have to generate examples?
I mean, that's how you get started off. But to me, when I look at this problem and I see, okay, well, I'm going to need to check if the lowest common ancestor of 2 given nodes, right? So then the next thing that clicks in my head is that, okay, what are the way these 2 different nodes can be arranged? And how can I view these relationships in a way that it's the amount of relationships I need to test is finite? So what do I mean by this? I mean, like, are they on, what if they're on different levels, same levels? That's one way to look at the arrangement of these nodes. But in the context of this question, I would say, okay, I'm dealing with ancestors, right? So then I would say, what are all the different ways these nodes can be related to one another in the tree structure? It's like, okay, well, what if they're not children of each other? What if one of them is a child of another? That's really, I just look at it in the context of the question.
Okay. Gotcha.
So it's like, it's merely thinking about what can go wrong, right? And of course, like, if you're like, don't know what the hell is going on and you don't really know the algorithm, then it's just like you're going to shoot randomly and try random examples. And that's kind of like where you're at. And so if you can really if you can frame the problem and really make your tests related to the problem, it'll make identifying all the possible test cases so much easier. And this applies to any problem, not just trees. Trees is just easier for me to express this idea with. But basically, it's like knowing that is that, okay, well, even if you want to try every single possible random example, then you probably would eventually come up with one being an ancestor of another. But to me, it's just like you needed to really understand what the problem is really asking. And to me, I was like trying to lead. I might have overhinted a lot of things. And so this may have contributed to you not actually understanding the problem as much as you should have. But overall, you should have easily gotten this within like 25 minutes. At least that's my thinking. You're doing this right. But the key takeaways I want you to do is to not get super hung up on your ideas. Make sure you understand exactly what you're testing, and to get better and faster at the call stacks. Be a little bit more atomic about the functions that you are leaving off at, and so on and so forth. Yeah. But overall, I don't see anything wrong with the way you did the call stack. I think it's fine.
Okay.
So this exercise, I'm happy that you did it. But right now, the next step is to focus on like this testing relationship, like understanding what you're passing in and what you're not, and being able to get through the problem faster instead of being hung up on your ideas. And I think that's the big crux of what happened here.
Yeah, it shouldn't have taken me that long to, especially with your hint about like the 3 and the 5. Like, I don't know why it took me so long to come up with that answer.
Okay.
Other than it just being hung up, yeah.
All right, give me like 2 minutes. I'm going to fill up on water.
Yeah, same. I'm gonna use the restroom.
Okay. Okay. All right, you back?
Yeah.
Great. Yeah. So my question now is going to be okay. Do you have any other questions for me before we go to the last problem?
No.
Okay. So I want this last problem. I want you to try and apply this testing thing again. We're gonna do another tree problem, but again, like don't get hung up on like bad ideas that you may have.
Okay.
I think we did root to leaf last time, right? Yeah, we did a symmetric tree. We did lowest common ancestor. Zigzag order traversal. So let's do find a root to leaf with specified sum.
Fuck. Alright.
Do you know that one?
No. But I do remember that. See, I think the funny thing with tree problems is like, if you think about it, it's like the idea is very simple, right?
Yes.
But if you just really can't memorize it.
Nope.
In my opinion, yeah. So
Don't fucking memorize problems, man. Figure out how to do problem solving.
yeah.
Okay.
But I just remember that problem was that problem
Okay.
it was tough. Yeah. All right.
All right. So find a root to leaf with a specified sum. So for instance, let's say I'm asking you for the sum of 38, right?
Mhm.
Well, there's two different ways I can do this. I can give you 10, 28, or 10, 13, 15. I feel like you did this problem for homework, but wait, did you do this problem for homework?
Let me check my folder real quick.
I think you did. Let me double check. Yeah. Oh, you did all paths. Yeah. It's pretty much the same thing.
Okay, we're gonna do another one.
Yeah, I'll do another one. Screw this.
Yeah.
How about checking if two binary trees are identical? Well, actually, that's too easy. I think maybe.
Yeah, that's like that could just be like the symmetric one, right? But it's just rather than mirror image.
I mean, if I gave you serialize, we don't have enough time for serialize and deserialize. Maybe we do. Yeah, let's do that. I'll give you the serialize deserialize problem. I love this one.
Okay.
Okay. So I want you to serialize and deserialize a general n-ary tree. So you see here, I leave the implementation up to you, but essentially I want you to actually figure out how you want to represent the tree and how you want to de-represent the tree. Yeah.
Okay. So serialize just means like, let's say, given whatever format these kind of like nodes come in, I'm able to construct like the parent-child relationships, right? Am I understanding that correctly?
Yeah. You're going to basically represent this as a string or binary format or however you want it to be, and then I should be able to read that and create a what's called a tree from that as well. So.
What's the input?
So the input's going to be a node. You have two functions. One's called serialize. Serialize, I'm gonna give you a node, and then deserialize is gonna be a string. So what you're responsible for is converting this tree into a string representation and converting that string representation into a tree.
Okay.
Does that make sense?
Yeah. Okay. So let's start with serialize first. And so if we're given a node, how can I represent this? Well, let's start with simple first. Like, how do I want to traverse the tree? This seems like to represent it such that you can deserialize and get it. I'm gonna go with DFS. Just
remember what I said before?
Yeah.
I mean, it's not necessarily wrong, but it's like, you sure about it?
Well, I guess the reason why is like I always just feel like DFS when it's representing like relationships, it seems to be the best in my head.
Okay, I mean, okay, sure. Let's say you go DFS. How do you want to represent that then?
Yeah. So let's just start off with A. Just did A.
Okay.
And then we have let's just say we had A and B, C. Oh, yeah. Yeah, well, actually, should I even care if it's DFS or BFS from the get-go?
Do you care if it's DFS or BFS from the get-go? Well, again, how are you going to represent the tree? That's the most important thing. These algorithms are really just in service of solving the problem, so...
Yeah, because right now I feel like the path of least resistance, like how do I want this to look first? Maybe.
Okay.
So, yeah, okay, we start off with A, and then we go into B. Actually, no, fuck it, we're going to do DFS. Yeah. So, fuck. Oh my god, come on. Okay, we hit B, and then if we're going with DFS, this just kind of represents like the connection between A and B. Like, if I have something like this, then like A is like B is A's child.
Okay.
And so it's just kind of like nested kind of parentheses, right? So.
Sure. Okay. So then, how do you want to represent B's child and C? And they have C and D as well to take care of. So how do you want to represent that?
So yeah, I guess first level it would just be A. Yeah, they're on the same level, so B, C, and D.
Okay.
And then going on to the next level, it would just be like E, and F.
Okay.
And then similarly, I, G, H, J.
Okay. And then you also have K.
Huh?
You also have K.
Oh yeah, and then for F it would just be K.
Sure.
So this is what we want to get.
Okay.
Right.
Fair.
Okay. So now it comes back to like how can I, since we're returning a string, there has to be some kind of way that for each node, like So we go from A. Let's just start with A. Okay. To recreate this example, it's like A. What do I want A to do? Okay. Well, I want to represent A's immediate children, right? So, well, let's just say we go A, and then we append. So node and get the value from node, and we want to basically right after like put node's children in parentheses.
Okay.
Yeah.
Sure.
Put node's children in parentheses. The common stuff I can worry about later, but right now just put the node's children in parentheses.
Okay.
And then for each one of those nodes, if they have children, like essentially, I want to be able to go into the node's children and essentially iterate this process again.
Mm-hmm.
So how can I connect that level, so to speak? So how do I go from A to B? Well, I know I said DFS, but it almost sounds like it's going to be like a BFS low key.
Mm-hmm.
So let's just kind of go with that idea real quick and see how that turns out. So pop nodes children off of Q, and I guess call function on that.
Mm-hmm.
Call function on that. And essentially we would do that for each level, and upon return, like closed parentheses. Just take a read through this. This makes any sense. So
Okay.
we get value from node, right? And then put node's children in parentheses, cool. And then whatever that node's children, wait, if I already put this into the parentheses, no, yeah, whatever.
If you put it into parentheses, well then you've already kind of it's gonna look kind of funny.
Oh, yeah.
You know, I mean, just actually try it out, like, because you have A, then parentheses B, C, D. You know, so
Yeah.
it's a little bit comic. So, is there a way you can do this better?
Yeah, so rather than just put them all into parentheses at one time, like I think this step could be put into almost like this part right here.
Mm-hmm.
So pop node's children off the queue, put that child into the parenthesis, and call function on that child. So what it would look like is basically like from A, we see that A's child is B,
Mm-hmm.
right? And we'd call like the function on B. And so then it would just get the value from that node and pop B's children off of the queue. And it would go to E.
Okay, instead of just talking about it, I would say right now try to actually should run through an example.
Okay.
I think it might make it a little bit clearer.
Okay. So we have A, and we have something called like Q.
Uh-huh.
Right now has B, C, and D.
Uh-huh.
Okay. We pop off B, so now we put B into the parenthesis, and then we call function again. And so now we have we're now at node B, and Q looks something like C, D, and yeah, this doesn't work.
Okay.
Yeah, this doesn't work. Okay.
So what are you gonna do?
Scratch that. Right now it doesn't work. Why does it not work? Because if I'm popping the children off the queue, like C is not the child of B.
Okay.
So that doesn't work. So the original kind of way I was going was, I believe what I'm trying to implement here is like kind of like a BFS kind of thing.
Yeah, it looks like a BFS because the moment you started introducing some kind of global queue, like that should have told you it was BFS.
Yeah, so it's BFS. So switching approach, I think it's not going to be that. So if it's not BFS, then it has to be DFS, or not has to, but you know, you go into A. Again. Well, let's. Oh my God. Okay. Start over. So we're at A, and we go to its first child, right? Which is B. So go to nodes child. Now, what do we want to do with B? Do we want to add it to whatever's like in the parentheses? So add B to string and go to B's child. And then if there isn't a child, so go to B's child. Now we're at E. You see E doesn't have any children. That's not. And a return back. I guess the part I'm kind of struggling right now to think about is we're trying to construct the string, and then we're doing this kind of like recursively. So we want to be passing in the string also.
Okay.
I guess recursively. So
sure. I mean, I would say just build a master string, but outside the function calls. But sure.
Oh yeah, that's.
I think you kind of forget this idea sometimes.
Yeah, that's actually a good idea. Fuck. Okay. Yeah. Okay. I think I have somewhat. I'm just going to write this down. So
yeah, go ahead.
Into pseudocode. So, at every node, right? We want to add it to, let's say, some kind of whatever the master string is. So if the master string started off add node value master string, and then go to nodes child. But before we go to the nodes child, actually, we want to add a parentheses to master string. Right. So from A to B, so we have that. And this will essentially go on until the node doesn't have any children, which is K, right? If no node child close out master string with closing parentheses, and so that's like for the case if there's no children. But then once we return back from this, A, B, and E, that we also have to count for F, because F is another is the other child. So I guess go to nodes child. Maybe a good way of doing that is just introducing like a while loop, something like that. Is like while child.
Sure.
While child. Go to nodes child. So go to nodes child. So B, E. So E, if there's none. Was a master string. So let me just run this real fast. So A, add nodes value. So A, so right now, A, go to A's child. We add parentheses to master string. and now while child exists, go into B, and go to nodes child.
Okay.
So then it would just be it would be E,
Mm-hmm.
and then E doesn't have any children, so this would return, and then we would go into the other child, which is F.
Okay.
And so we have E, F has a child, and it would be at K, and K doesn't have children, so now we start closing it out with the closing.
What's the value of the master string then at each one of these?
Each step of these. Oh yeah. So
yeah, keep in mind. Remember when doing the stack trace, you want to remember which step you're on, because
Right.
like you see how like it's actually pretty useful to know which step you're on here.
Yeah.
Yeah, like I don't know where the fuck you're at right now. I mean, I do know where you're at, but because I haven't paid attention. But it's like for your own record, I'm pretty sure you're gonna forget.
Yeah. So.
Okay, it's gonna be 3. We have 3 minutes left. I kind of want to do a quick recap of what we talked about today and give you some homework.
Sure. Yeah.
Okay, so basically we talked about this idea of testing for states. I really want you to really try this idea when you go do your problems. Now, and we'll go into your calendar later. But I really want you to not get hung up on your ideas. I think this is what's killing you. Get better and faster at the call stacks. Remember to write out which step that you're at. Write out what the values that you're passing in and out of, and really be atomic about it. Every single little detail should be like done. Every single step. So when you say, "Hey, yeah, I'm gonna found LCA and assign a value to it," I want you to actually express that in the call stack. Because I think if you have this tendency to skip details. Don't skip fucking details. Like they're really important, and they like one little detail miss can screw up your entire attempt. So for homework, I really want you to actually do this problem and do a write-up for it. Problem. And write up what you could have done better, how you got the problem solved, etc. So like the same way you would do a replay analysis for me. I want you to do a write-up for this one, and we'll go over if you feel like this is a good candidate for us to do a replay analysis on, then record yourself. But I would recommend at least try the testing idea on some EPI problems before you do the homework.
Okay. Oh, okay. Sure. Yeah.
All right. So let's go to your sheet.
The study plan schedule.
Yeah, study plan. I want to see where you're at.
Yeah. So actually, if you scroll down to I think row 34, it's that's kind of where I'm at for the EPI problems with binary tree. And
all right, let me open up again. I'm trying to. Okay, cool. Yeah. So you're at so I'm looking at row 2024 to 1030. I'm looking at the study plan schedule, by the way, just for the sake of. So let's actually look at the book. So looks like you did tree, depth research, breadth research, subsets. How close to finished are you on EPI and grokking?
Yeah. So for the breadth research, I did all the problems excluding the challenge.
Okay, that's fine.
Ones. Yeah, let me pull it up real fast.
So I'm going to mark that as done.
Yeah. For the where the fuck are we? Depth research. Okay, depth research. I have really just 2 more problems left that I wanted to do the kind of like the talking it out and like the other process with, which is the path with given sequence.
Fine.
And count class for some.
I also want you to try the testing idea with it as well.
Yeah. So those 2, and then for the EPI problems, I did the C0 and C1.
Okay.
For the binary tree chapter, all that's remaining is 9.12 and 9.11, and both of those are in. They're like the C3 and stuff like that.
Okay.
Yeah, 9.12 is in C2 and 9.11 is in C3.
Okay,
so 2 more problems in the EPI for binary trees, yeah.
Okay, fine. That's fair. I want you to finish those up. So finish up depth research tree from last week. That's cool. What about subsets? Did you get a chance to do that?
Subsets with the new patterns or with what you kind of taught me. No, I hadn't had a chance to touch that yet. I've only done, but I've only done like one problem from that.
Okay, so I want you to do that subsets. I think it's gonna be pretty good, because then you're forced to test stuff. I also want you to do more EPI if possible.
Okay.
So then, for
Yeah.
EPI, I want you to do the recursive chapter. Did you get a chance to touch that?
Was it actually chapter 18? I kinda looked at
In
it.
my book, it's 16, but the
I have the Python
title
version.
the title of the chapter is recursion. So
Okay, sure, we can do that.
then have you done that or not?
No. I was going to look at the introduction of chapter 15 for recursion.
Okay. So recursion according to you is 15. That's fine. I really want you to nail this down.
Okay.
And so after that, yeah, let's see. Binary search trees might be good too.
Okay.
Yeah, we'll do binary search trees.
Sure. And also just like I kind of noticed this. I do feel very unconfident low-key with arrays sometimes still.
Okay, then let's do this. Let's switch for chapter 6 arrays then.
Okay.
Because I want you to, like, arrays are tend to be pretty hard. And I want you to really keep in mind, like, not only just talking out your idea, but figure out how to test it as well. You go through, if you go an array with those two, and you practice pretty well, I think you should be fine.
Okay. Yeah, I mean, we don't have to do those this week, but I just thought I'd mention it, like, that I feel very kind of weak in terms of arrays. Yeah.
Because the thing is that we only, like, after this week, we have, like, 2 more weeks before we start scheduling your phone screen, for your first phone screen. I really want you to be, like, nailing down arrays and strings like no tomorrow. I want you to be, like, almost, like, 70-80% of the way there.
Okay.
So if you're feeling very weak on it, then we can handle it. But finish up all these other recursive things beforehand, and then hit the array.
Okay, sure. Sounds good.
All right, I think that should be good enough for all the work. Any other questions?
No.
All right, sounds good. Then I will see you Thursday.
Yeah, see you Thursday, Edbert.
All right,
Good night.
bye-bye. Okay, cool. So that should be it. I will take questions from the crowd. Let's see if I can find out where the where I put the tab for the.
How do you weigh?
Hacker News? Nope, that's not it. Man, where did I put the tab? Alright, so. Have I solved this last problem on a YouTube video? No, I haven't actually put a YouTube video on this problem out for the, what's it called? The serialize and deserialize. I think, no, I did actually. I did put a video out. Hold up. Yeah, I put a 2-part series out, actually. So I put one of me solving the problem, and then I put one of me actually, what's it called? Of me going over the mistakes. So in case, like, you guys haven't seen it, I'll link it in the video here, so. Yeah. And if there are no other questions, though, I guess we'll call it a night. Thank you guys for watching. We'll be back here on Thursday, 9 p.m. And we'll go over some replays with my client here. And we'll also have the client for Monday as well. So with that, have a good night, y'all.